There, starting the recording. That makes it official. Hello, Zoomers. 2 hands a wave. Hello, Roomers. Hello, everybody. The doorbell will continue to ring, but that's just how it goes. Let me start the screen share so the Zoomers can see what I see. There we go. What I did yesterday is get the homework system up and running so you can do homework 0 and earn your 2 points of extra credit. I made a video for the other class since most of them haven't seen it yet, and you can follow along with the video if you need to, or you can do it on your own. So it works the same way as usual for those of you who've had the homework before, with the exception that it works on all the browsers this time. So Jonathan figured out the weird security issue that wouldn't let it load for certain browsers, and it appears to be working just fine on everything. If that changes, if you encounter any sort of weird error messages or it doesn't load properly, please let me know so that we can try and troubleshoot it as quickly as possible.
Lisa,
Yes?
I actually just tried logging in and there is some weird error talking about database engine nonsense.
Database engine nonsense. Okay.
The nonsense is my addition.
Somebody put it in the chat.
Okay. So this means that we are missing a database that you need to do this. And the question would be why? So that is actually my problem, not yours. I will work on fixing that and let you know as soon as it's fixed. But this one I've had before. This is a screw up from me. I can handle this one. So I was going to do a demo, but now that I can't do the demo, the only thing I was going to remind folks is when you go down to the bottom of the screen and it says submit your answers, there's one more step after that. You have to enter your 8-digit ID number again to actually submit. That keeps people from hitting that button accidentally. That being said, if you ever do hit it accidentally somehow or otherwise realize after the fact that you want to change an answer and it's before the deadline, let me know and I can reset your entry so that you can have your responses active again to change them as you wish. So sorry about that. It did work for the other class though, so I get like maybe partial credit or something. I also spent the morning fighting with R, so you know I'm in one of those feisty kind of moods, and I'm happy that I just get to talk about concepts today, because concepts are a lot more fun than code. So we have the remainder of the review lecture to do, and that will help you in completing. I was also going to point out the first real thing that you have to do is homework 1, which is a Word document that you can download that has 10 questions. The questions are taken quite literally from the textbook review questions that I had to write to the end of the chapter. However, I never wrote answers. The publisher wanted me to write answers and like stick them someplace, and I refused. So the answers are in my head and hopefully in all of your heads. But as we go through things, you might, if you haven't grabbed the document, take a look at it and sort of make notes to yourself like, okay, this is where this part is, this is where this part is. I tried to give you hints with respect to what chapter things are in, but all of these points are something that we will hit as part of this review and or were covered last semester in greater detail. So just to remind you, the process for homework 1, you have that effort, I'm calling it an effort draft due in a week and a half on the 30th of January. You get 5 points for attempting every question, half a point per question. I'm not going to read your answers, I'm just going to see that you did it and give you the points. Then on Thursday's class, we will discuss it, go over the answers. That way you can revise your answers as needed to make them more correct and or complete. Then the final version of it will be due 3 weeks after that. So you have a little bit of time in there to work on those things. And then you get 5 more points for being correct in your answers as well. That class, by the way, comprehensive exams are scheduled potentially in this room, and so I have us meeting on Zoom only, but I'm waiting to hear back from the people. If they don't need the room, then we can be in here instead. But they get first dibs for whatever reason. So, any questions on that stuff? Okay, then bye-bye webpage. Hello, PowerPoints. So we'll continue diving back into the world of longitudinal here. So where we left off was the idea of trying to model person dependency. Now, depending on your perspective, person dependency is either a nuisance to be solved or the whole point of the study. Person dependency is the idea of commonality in how people change over time. So we can model that by letting occasions from the same person just be correlated. That's one strategy. We can model that by letting, basically estimating a separate fixed effect for a per person dummy code for who's who. That controls for dependency, but it doesn't allow you to predict why people differ from each other. So the approach that we're taking predominantly here is the idea of adding a level where we treat occasions as nested within persons, and then we use random effects to describe all of the ways that people differ from each other systematically in their initial levels and their change over time, and potentially in their effects of time-varying predictors besides time. So that's where we are to start with. So intercepts, first thing here. So if we go back to general linear model land, so the idea that we're predicting one outcome at a time, we have the fixed effects in the model of the means, which will be estimated constants. The model for the variance then in a general linear model only has E. So it has one source of variance left over after controlling for the predictors, because this model was designed for only one dimension of sampling at a time. Furthermore, the E's are supposed to be, besides independent, that's the idea of one dimension of sampling, they're supposed to be normal and have constant variance. Now, those latter two things, I am not planning on changing this semester. I had to make the call into what all could fit into one semester, and generalized multi-level models did not make the cut. However, this is the however finger, by the way. This is the although finger. However, in the fall, I am teaching the clustered version of multi-level models, and I do have an extended unit on generalized models there. And it's also still there from the last time I taught that class in 2019. So I have examples, I have resources I can send you if you need to predict, say, a count outcome that changes over time, or an ordinal outcome that changes over time. If you understand how to do that for just independent observations in regular generalized models, it's not that different in multi-level. It's just a question of putting that all together. So for this semester, we're leaving the idea of normal and constant variance alone with respect to the residuals and focusing on just the idea of violations of independence or ways that people differ from each other. So back in the day here, empty model, no predictors, one pile of variance to start with for GLM. If we change that so that we have 5 occasions per person, say we have data that looks like this, where the black line is the mean for the sample. These are individual trajectories for an outcome that fluctuates over time rather than changes. If we just fit a general linear model with one pile of variance, one variance component, that would be like saying E has to represent everything from where the sample mean is down to where each person's observation is per occasion. So there's no separation or demarcation of reasons for deviations from the mean. First thing we're going to do is introduce a random intercept, which is this U0 here. It has an I on it because each person gets their own version of it. And U0 is a way to introduce person dependency into the model. U0, the random intercept, says that people differ from each other in their mean levels, and that's why the observations are related. So once you allow for a constant difference from the sample mean to each person's mean line down here, then the E's are supposed to have constant variance and be unrelated. Now, if people differ from each other in more than one reason, that's not going to be true, but this is our starting point. So, critical idea though, we have not explained anything, cough, cough, homework question. And yes, you can search the YouTube videos for cough, cough, homework question, and it will find where I do that in the videos. We have not explained anything. We have partitioned or distinguished or said that part of the variance is, what's the word I used last time? Can't come up with it, starts with an A. Attributable, that's it. It's going to say allowable, but that's not right. We can say however much of the variance is attributable to person mean differences, and the rest of it is attributable to within person fluctuation. But that's not the same thing as explain, at least to me, and I will die on that hill. There are other people who would disagree. But to me, it's like, well, we don't know why people need their own means. So you haven't really explained anything yet. You just know that they do. So this U here is what then is allowing the E's to become more like the E's in general linear models. So this partitioning process then has vocabulary that goes with it. If we think about a traditional longitudinal model of relatively few occasions nested in persons, we would say that the variability across people in the U random intercepts is at level 2. It's between persons, it's inter-individual differences. It's cross-sectional. So random intercept variance is a cross-sectional source of variance. It's what would have been there had you measured someone only once. The mean is probably a better indicator of a person's overall level than any one observation would be, but conceptually it's still just cross-sectional. Level 1 then is the E deviations relative to where the U prediction ends within persons intra-individual time-varying information. So that's the extra part that a longitudinal sampling design affords you. So then to put equations on that, an empty model before we introduce multi-level notation would look like this. Beta 0 is my fixed intercept. U0 is a random intercept, and E is a level 1 residual. Beta 0, once you add the U random intercept, becomes the mean of the person means. So it's not going to be the same
I
beta.
have a question.
Yeah, hit me.
So when we're talking about the fixed effects, like in practical example, is time or like occasions treated as fixed effects or people?
It depends on how you want to set up your model. Either or both could be.
Okay.
So
if it's like a time-only model, then it would obviously just be time would be the fixed effects.
A time-only model, meaning
Or,
time is the only predictor.
I'm trying to think of the terminology we used last semester. Like if we only have time incorporated, but like
Oh, unconditional.
yes, yeah.
Yeah, your unconditional model for time has all the stuff related to time as a fixed effect, as a random effect, and any additional correlation in time-specific residuals.
Okay, that makes more sense.
Okay, cool. So yes, so my point was the beta zeros won't necessarily match, but they'll be close because it depends on if people contribute a different number of observations, then one is differentially weighted. All right, then in matrices. So this idea of two piles of variance then, behind the scenes works a little bit more complicatedly. So this is our vocabulary review in terms of the pieces of information and how it all fits back together again. So the sources of variability in the model that are across people at level 2 live in the G matrix. At this point, we only have one source of variability, the intercept variance, and so the matrix is just a scalar, a 1 by 1. The R matrix then holds the remaining E variances and covariances over time. And so this is like a per person idea. If I have 5 occasions per person, this is what it would look like. Now, if it's only one person, this can't possibly be a variance because this is just one number. So we're borrowing across people to get an E variance at each occasion. This basic model assumes that the E's are unrelated. That's why there's zeros everywhere here. And it assumes that E has the same variance across occasions, which is why the diagonal is just one symbol. Putting these two back together again, if you take this random intercept variance and just like stick it everywhere in here, you get this combination at the top. So G and R put back together again equal what's known as V, which is the marginal or combined total variance covariance matrix across time. In 2 weeks, we're going to call this sigma in SEM notation. It's the exact same idea. The model predicted variances and covariances. In an SEM context, it's typically across items. In this context, times are items. That's the connection between the two. Now, those of you who are better at math than me are like, yeah, Lisa, just take the intercept variance and stick it everywhere is not a viable matrix operation. And you are correct on that point. So what happens behind the scenes is that G gets pre and post multiplied by another matrix, which is Z, cough, cough, homework question, and that holds the values of the predictors to be given random effects. In this model, Z would just be a column of 5 ones. So you have 5 ones going down, and then you shove it over on its side, and you have 5 ones going the other way. That makes the G matrix the same size as R so that you can add it to V. The other thing that it does is ensure that we have the right size of matrix for each person given their individual data. So if I have a study where some people have 5 occasions and some people only have 3, their V matrix would be 3 by 3 instead of 5. And a comment, did we go over Z matrices last semester, or is this new? We went over them a little bit, I would say. We're going to re-go over them. Yes, you introduced that term to me last semester, I think. We're going to re-go over, which means in more detail than review, once we get the random slopes here in just a minute or two. Okay, and yes, this is in Chapter 4 and also in Chapter 5, how this stuff fits together. Chapter 4 only has random intercepts as a starting point, and Chapter 5 adds random slopes. And then Chapter 6 has a bunch more of these things for different types of models of change, polynomials, piecewise, etc. Okay, yeah. How are we doing so far? Am I talking too fast? I've had a lot of caffeine today, so you can't fight with R without a lot of caffeine on board. That's what I found. All right, so the purpose of an empty model like this, it's not because we think it's going to fit well or because we think it's going to be adequate. It's a reasonable starting point for longitudinal data. One of the things that we would compute out of it is our friend interclass correlation, which you can think of 2 different ways. One is that it describes the proportion of total variance that is between persons due to the random intercept variance at level 2, due to mean differences there because of cross-sectional variation, all of those words. The other way to think about it is as the expected correlation of occasions from the same person. Next fall, when I teach these exact same models for clustered data, the latter is probably going to make more sense. Like if you're thinking about kids nested in classes, how related are kids from the same class? That's interclass correlation. How related are occasions from the same person? It means the same thing, but it's weird because an occasion is not like an entity, the way a child is a separate entity from a classroom. So either way you want to think about it, this is a barometer of how much variation there is to be explained per level. Yes, sir?
So like in the classroom context, you would say the proportion of variance due to classroom membership or group membership or something like that?
Yeah, so if students are nested in classes, then we would say that the level 2 variance is classroom mean differences. And so an interclass correlation would say what proportion of the variance is due to what class you're in, what proportion of the variance is due to some classes performing better on average than other classes. People might want to be like, that has to do with the teacher, but given the fact that teachers are not randomly assigned to classes, I don't think we can make that inference. Has something to do with the group you're in. In this context, it has something to do with the person you are, and that you are the same person all the time. We can do a significance test to decide whether or not we need random intercept variance. That's not something you would typically do in longitudinal data, but it is something you would do in clustered data. Like, do I even need a multi-level model? The answer is always yes, by the way, but if you need to put some numbers by that, what would I do to test whether or not the random intercept variance adds to the model, whether I need it? What kind of significance test do I need for that? Starts with an L.
Likelihood ratio.
There it is, likelihood ratio test. The difference in -2 log likelihood from a model that has the U variance versus a model that has only the E variance. Anytime you want to answer a question about what kind of variance you need in your model, it's a likelihood ratio test. Otherwise known as a deviance test, otherwise known as a chi-squared difference test. They go by a lot of different names, but -2 times the difference in likelihood, log likelihood, excuse me. Yes?
Doing this, we are trying to have better standard errors for the fixed effects, right? Doing
Yes, but that won't be enough to the extent that this doesn't adequately describe the variance and covariance over time. It's better than pretending people are independent, but usually this is insufficient. People differ from each other in more than just intercept in a lot of cases. Where I was going, though, I remember now. Beyond a significance test, an interclass correlation is an effect size. So you can get your chi-square significance test that says, you know, my model fits better, p less than 0.01. Well, how much is that? Well, just like everything you ever learned about power and significance tests and effect size, if you have a lot of people, you can have a very significant result that's not that big in an absolute sense. So intraclass correlation is an important supplement. How much of the variation is because of person mean differences, proportionally? It also helps to tell you then what kind of predictors are going to be more or less useful. If you find that more of your variation is between persons, you need time invariant predictors to capture that. If you find that more of your variation is within persons, you need predictors that also change over time within persons. All right, so slopes then. So time, then, adding time to the story here. Basic vocabulary to go with this, the idea of fixed time slopes versus random time slopes. A fixed effect is a constant. A random effect is a variable. It boils down to that in its simplest form. But the thing we're talking about is a slope at this point. So if we look at just linear time to start with, here's a picture of what it would look like if the x-axis is time, the heavy black line is the mean for the sample, and then these would be individual trajectories where the dots around the trajectories are not shown, just to keep the picture understandable. This would describe a data set in which the outcome has neither a fixed effect of time present nor a random effect. There's no fixed effect because the average trajectory is flat. The time slope is indistinguishable from zero to the best of my PowerPoint drawing ability. There's no random slopes because that no change slope works well for everybody. People don't need their own. The aggregate is good enough. This is what the empty model assumes. If all you have is a fixed intercept, a random intercept, and a residual, this is what you got. If we have a line that's not flat, then we would say, yes, there is a fixed effect of time here. But there's still no random effect in this picture because everybody changes to the same extent. These are the only two pictures on this page in which a univariate repeated measures ANOVA would be okay. These are the only two pictures in which the variance doesn't change over time because these are parallel trajectories. The bottom two then, no fixed effect but a random effect. Yes, that can happen. On average, there is no change, but that average trajectory is somewhat misleading because some people go up and some people go down, so people do need a random effect of time to differentiate themselves from one another. That causes the variance to change over time as well, and it will also change the covariance over time, although it's not shown in the picture. And then D, you can have both. So there can be some degree of change on average and then some degree of individual differences in change around that. So if we put multi-level notation onto those ideas, subscripts are everything. I used to think they were overkill, and now I understand the error of my ways. I am pro subscript. So if we change from an empty model in a GLM where it's one observation per person to a traditional multi-level notation, then we switch from y sub I for one per person to y sub ti. By the way, these letters are my choice. You can choose whatever letters you want. It does not have to be ij. It doesn't. I don't know where like that started, but you are allowed to pick whatever letters you want. Don't make them the same letter, right? Like students in schools, you can't have two S's. That doesn't work. But you could do KS for kids in schools or pupils in schools. That's sort of a European version of it. When I write generic papers about multi-level models where I'm deliberately trying to be ambiguous, I do WB for within and between. That works no matter what you're talking about. So if I have like a simulation where it doesn't really matter what the context is, it's WB for me. So TI, because it's time with an individual. So beta 0I is now a placeholder. It is not a parameter. It is a backpack. It is going to carry the ingredients by which each person gets their own intercept. Where now the notation is this wide-looking thing is gamma. That's our fixed intercept, the mean of the person means. U0I is our random intercept for the deviation for each person's intercept from the average intercept. You feed those two together into the level 1 model, and then E sub TI picks up the rest. And if you want to see it in composite notation, this is what it would look like. So the composite equation matches more readily what it looks like when you put the model in software, right? You just list out, these are my fixed effects, these are my random effects. The multi-level notation makes it easier, I think, to understand what goes into each way that someone differs from each other. Does it have a fixed effect and a random effect? Does it have predictors? Are the predictors predicting each aspect of the trajectory or only some? So there's not necessarily a right versus wrong way to express these models. As long as you are clear in what you're doing and you describe your notation, then you're allowed to do it however makes the most sense. When I get to crossed models, by the way, I don't do this anymore. I just do composite notation, because cross models, when there's more than one level 2, that's ugly. So, but I've even, like, across the papers I've written, I've switched it back and forth. I've changed letters. You can do whatever you want so long as you are internally consistent. That's my perspective. In terms of the number of parameters in this model, there's only 3. Because this idea that each person gets their own U is just an idea. What we actually estimate is the variance across people of the random intercept U's. So no matter how many people we have, a random intercept variance is 1 parameter. This model says that the E variance is the same over time, which is why it's only 1 parameter, but it could be more than 1. You are allowed to ask whether E has different variance across time after controlling for the intercept. That's a reasonable question to ask. So you could have potentially as many E variances as you have occasions. That is the default way it gets set up for these models in structural equation modeling. They start from a perspective of each box gets its own residual, because they're used to thinking about boxes as items rather than occasions. Okay, how are we doing? Thumbs, slow nods. Somewhere between here and here is the goal. Okay, zoomers, anything from you? Winky thumbs. Oh, they move now? I didn't know that.
Yeah, the reactions move.
They move now. That's exciting. Okay. Learn something new every day. All right, so this one is A. This goes with the A picture. So we're moving through the rest of the grids here. B is this one. So if we add a fixed effect of time, because time varies over time, it goes in level 1. And I don't mean to sound stupid when I say that. I'm making a point. Because the rest of the semester, when we add predictors, that'll be the question. Does it vary over time or does it vary over people? Because that's the first step to figuring out where it goes. So time is TI because each person could have their own set of time observations. Beta 1 is going to be the slope placeholder for how each person gets their own time slope. This is linear in this idea here because time is just like time, 1, 2, 3, 4, but this could be anything. Next week we'll talk about what are the pros and cons of having something like age or grade in school or time since diagnosis. But if you think of it as 0 is when you started the study, and then how much time has passed, that's just time. So down here then, because we have 2 beta placeholders, we have 2 level 2 equations. At this point though, the beta 1 placeholder is only holding the fixed effect. So these are equivalent in this model. So there's no random effect yet. That means this model says everybody changes the same. Which of my 2 piles of variance should have been explained by this new fixed time slope? E or U? Those are your choices. One vote for E? Anyone else want to vote for E? Yeah. Yep. E is within person fluctuation over time. Part of that could have been explained by giving everyone a non-flat trajectory rather than a flat trajectory. That should reduce some of the E variability. So we can compute a pseudo R-square for how much of the E variation has been reduced by a fixed slope of time as an effect size to go with our significance test. So this model then conceptually looks like this. Parallel trajectories. The V matrix would still have what is called a compound symmetry form, equal variance over time and equal covariance over time, because the only source of person variance here is in U0 still. So this model says people only differ in their intercepts. A logical consequence of that is that the intercept variance would be the same at the end of the study as it is at the beginning. So you can think of this as like person mean differences still, even though it's an intercept, because it's just a constant shift over time. That changes once you add a random time slope, which is this one, slide 28. So what's new in the model? We'll play Where's Waldo, equation style. Where is it? U1. Where's U1? Gotta find it. In. Right here. There's U1, and it's also right here. So now there's a symmetry in how the betas are constructed. Each has a fixed part and each has a random part. U1 is the discrepancy between the average line and your line in terms of the slope. In adding U1, how many parameters have we added to the model and don't say 1? 2. What's the other one that's sneaky? Covariance. Now, is that a default or not? When you go to estimate these models, does the covariance come along for the ride by default or not?
Default?
Default, if you're using R. Yeah. If you're using SAS, no. If you're using Stata, no. If you're using SPSS, no. If you're using R, Elmer, yes. LME, yes, I think. And those are the only 2 that I know for multi-level.
So the other software produce correlation?
Say that again?
The other software, they produce correlation.
It produces it in a correlation metric in the results. But in order to get the correlation, they would have had to have estimated either that or the covariance. So you either will get back like variances and correlations or variances and covariances, but you can get back and forth because correlation is covariance over variance, basically. So yes, that's something to watch out for. This is somewhat of a debate, but I think most people would agree that if you have a U0 and a U1, an intercept and a slope, and they're about the same person, probably they're related. Like that's a reasonable thing. The other thing to keep in mind is that U0 is now conditional. So the idea of this is the expected blah, blah, blah when predictors are 0. The fixed intercept becomes conditional on time 0 as soon as you have a time slope as a fixed effect. The same thing is true on the random side separately. U0 is conditional on time equals 0 once you add U1. That means that if you have a time metric that makes no sense, you could end up with estimation problems. Like if you had time as like chronological age, and age was for older adults like 80 to 100. If you didn't center time, then your intercept variance would be for newborns based on a sample of 80-year-olds, and that's not going to work. I've seen it literally cause the model to blow up, and that was why, centering. So keep that in mind when you're thinking about what time is. 0 needs to be in here somewhere. That way your intercept has meaning as at time 0 specifically. All right, so do you want to do the pieces real quick? Would that be helpful? Okay. So this is the composite equation then. The black line is for the mean of the sample, the blue line is for one person. So fixed intercept, note the scaling of time on the x-axis here, 0 is the starting point. So the fixed intercept is the predicted outcome from the line at time 0. Not the actual time 0 mean, but the line that goes through the means where that ends up. This blue person is below everyone else when they start. So their U would be -4 to get them down to their predicted intercept, which is about 6. So U, if it's negative, you're below everyone else. If it's positive, you're above everyone else. The slope for time, rise over run, change in y for a 1 unit change in time. That's 6 according to this picture. The blue person is growing faster than everyone else. So their U1 slope is a +2 deviation. That makes their total slope 8 when you put it back together. If their U1 were negative instead, does that mean that they went down? Not necessarily. Like if their U was -2, how would I talk about their type of change?
Slower.
Not slowing down. They're still going up, right?
Lower than the mean.
Yeah, lower than the mean or up less. Because their rate of change would be 4 instead of 6. Yep. Question?
No,
No?
I'm just talking in calculus. It's
Talking in calculus? Okay. Are you speaking Italian with your friends? Is that what's happening here?
Yeah, all my friends just.
Yeah. No, that's like a line from a movie. Jonathan always makes that joke. Whenever he talks stats, he's like, I'm going to speak Italian with my friends. It's like The Godfather or something, right? Does anyone know what I'm talking about? No, it's a thing, I promise you. Somebody look this up on the Google. Yeah, like it's, I'm going to speak Italian with my friends. It's a famous line. It's one of the Godfathers. I've never seen those movies because I don't like movies where people get shot. But this discussion, though, makes another homework point, as we do this here, that these fixed and random effects are hierarchical. Which comes first? Fixed. Can you have a random effect without a fixed effect to go with it? No. It doesn't make sense. Random effects are deviations. If you omit the fixed effect, you're saying it is exactly 0. That could be true, like it could be non-significant and not differentiable from 0 at one point in your modeling process, but if that were to change, not having that fixed effect in there is going to cause problems. In the world of SEM, fixed effects are going to be the means of the latent variables. So beta 0 and beta 1 are going to be latent variables. The means of those latent variables are your fixed effects. Their variances are the U variances. So it works the same way in that world as well. Last but not least, E is the difference between where your line ends up and where you were at that particular occasion. So like E would be negative right here because they're below their predicted line. E would be positive for this second occasion, negative again, and a little bit negative. So E is where are you off your line today? How many occasions do I need to have both a random slope U1 and an E residual left over? 3. Yep. If I only have 2, you cannot differentiate what is real change from what is error. That's why pre-test, post-test studies are a bad idea. They are the minimum entry to being longitudinal, but you cannot differentiate individual change. If you've heard of latent difference scores in SEM, nope. They're not latent. They shut off the residual variance at time 2 so they can estimate the change variance instead. It's a sleight of hand. 2 occasions is not enough to differentiate individual change. Okay, where are we at? 111, doing okay. So, matrix time then. How does this work under the hood? This idea that everybody gets a different slope is all like nice and conceptual. It's easy to think about it that way. It guides a model building process because there's a logical consequence. Well, people start out differently. Why? Because of person characteristics that do not change over time. Some people change faster than others. Why? Because of person characteristics that do not change over time. So how does this idea that we have 2 different sources of dependency, 2 different reasons why the observations within a person were initially correlated, how does that play out in the math? So we have changed our model from having only 1 term as a level 2 variance to having 2 of them. So at this point, if we have a random intercept and a random slope per person, what we're actually estimating is the variance of those intercepts and the variance of those slopes across people. They get a covariance to go with it. So our G matrix here at level 2 is a 2 by 2. 2 latent variables, as it were. As I have it here, our R matrix is still diagonal. This would be an independent structure, I think in Stata is what it's called. There's a bunch of different synonyms, but this is like the default in almost every package. And this is the only choice in Elmer, by the way, which is why last semester I ended up having to switch back and forth sometimes between LME and LMER, which are in different packages, even though they sound the same. The GLS and LME functions within the NLME package have options for what can be an R, and LMER does not. That it runs faster as a consequence of that simplification. So this structure says the E's are unrelated, and it says the E's have constant variance. It's not saying that occasions are uncorrelated. It's saying that occasions are uncorrelated after controlling for the stuff that's over here in G. So it's just the level 1 within person fluctuations that are unrelated over time, and that's a testable hypothesis. So G is level 2, all the reasons people differ from each other. R is level 1, all the remaining variance and covariance over time. Putting them together is going to be the V matrix that's marginal. So this is what we're talking about here, different slopes for different folks. If people change differently, the total variability in the data has to change over time too. So does the covariability. So that's actually what G is doing. When we add a random slope, we are introducing heterogeneity of variance across the predictor the slope is 4. Now I've said that slowly because I'm saying it in a generic way in this context so that we can add to that idea later. Introducing a random slope introduces heterogeneity of variance across the predictor that the random slope is 4. In this case, it's the time predictor. In a month, it's going to be like within person stress. It's the same idea though. So the Z matrix then is each person's values for the predictors to be given random effects, where the first column is for the intercept, the second column is the particular time values that a person has. In a month or so, these might be stress values or anything else that fluctuates within a person that you want to see if there's a random slope for. So we take Z, kick it over to its side to make the transpose. That makes the result a 4x4 matrix that you can then add to R. And then V has a very complex structure at that point. The diagonal is given by this equation right here. So I want to point out the variance over time, the end and the beginning, you know already. Intercept variance, stuff, residual variance. Like that's the basics of compound symmetry without the stuff part. The stuff part has time in it in two places, as a multiplier squared of the random slope variance for time, and twice times time in the covariance between the intercept and the slope. That's a long way of saying it's creating a time-specific variance, and the time squared is making it change quadratically. So it's a U-shaped function of how the variance changes over time. There's some point at which the slopes will all converge onto some minimum variance, and it spreads out from there. Likewise, covariance between occasions in a compound symmetry model was just due to the random intercept variance, saying that the reason the occasions were correlated is because of person mean differences, but now there's extra stuff, where A and B are the particular occasions for which we're computing a covariance. So the covariance is also time-specific as well. So this idea that variance and covariance become functions of time is why we can have different occasions per person. So Z is the individual person data that controls the times that the model is predicting that variance and covariance for each person. So we can have a predicted variance at time 1, 2, or 3 if that's what we have. We can have a predicted variance at time 1.86. Same thing with covariances. It's a function. So we use whatever data they have, and each person potentially has a different V matrix. So unbalanced data then, this is the point at which traditional assessment of model fit in an absolute sense is not possible. If you have different occasions per person, there's no common matrix to come back to that you can say this is the right answer, like you could if it were an unstructured matrix. So there are many situations in longitudinal models where you won't have any kind of right answer. You just have to kind of stab in the dark and do the best you can. Okay. Here's a picture of what it looks like to build V out of the ingredients for two people at the same time. So Z then, person 1 is the purple box on the top left, person 2 is the purple box on the bottom right. This type of structure is called block diagonal, like stuff, zeros elsewhere. So the second person has different occasions than the first person, and they have only 3 instead of 4, fine. They get a different predicted V matrix at the end of this chain for their little section. G is shared, so we assume that these variances and covariances hold for everybody. That's an assumption as well. R, right here, is a simple diagonal structure, meaning that the variance is the same across time and no covariance. That's also an assumption. It's the same for everybody and the same for all occasions. The off circles, nope, those are zeros, Lisa. It's time to have a little more caffeine if I don't know the difference between 0 and 0. Where I was going is, what do the zeros here mean? Conceptually, what is being said by putting zeros between people?
They are independent.
They're independent, yeah. What if these are like two kids from the same classroom? And you have lots of classrooms. You gotta put something there, right? You gotta put something that would let two kids from the same class have something that's not 0, but then people who are in different classes could still have zeros. That will happen by adding a third level. Another U variance at a higher level that would allow people to be correlated. That's the end of this semester. What does decimal time mean? This would mean, like, if this were, 0.2 weeks later, 1.4 weeks later, 3.5 weeks later, we want to keep the amount of time that has passed as specific as possible in most cases. It's an empirical question whether you could simplify that to just 1.4 is close enough to 1, it's fine. All right, yeah, so big picture. The idea of adding in random effects allows for correlations between occasions. Adding in random slopes adds for heterogeneity of variance and covariance across occasions, and any other predictor that is measured at level 1 if we did that too. So unstructured is your best possible model if you were to just let all of the occasions have their own variance and have their own covariance. You can only do that if everybody has the same set of occasions. Compound symmetry is the simplest model for longitudinal data that would be plausible, but you can always estimate it no matter how many occasions you have and which ones they are, because time is not involved. This side over here, by the way, compound symmetry, is the univariate approach to repeated measures ANOVA. Unstructured is the multivariate approach. But when people use those words, they typically mean least squares, which means you have to have complete data or the whole person is kicked out of the model. We're using likelihood instead so that we keep whichever occasions we have that are complete. All right. Yeah, words. So, big picture, we are accounting for person dependency with respect to time. There may be other sources of dependency with respect to other predictors. We would handle those in a similar fashion, potentially, of having random slopes for those as well. It is my strong opinion that time comes first. We get all of the patterns related to time in the model first before we look at how a variable relates to something else. Otherwise, that other predictor is trying to prop up some of the dependency over time, and that's a recipe for disaster. Looking at you, autoregressive cross-seg panel models. That's like 2 months from now. Okay. So, step by step then, in terms of where the variance comes and goes. Once upon a time, there was an E. First thing we do is split it. So we have level 1 residual, level 2 between person intercept variance. The two of them added back together again are going to come close to what you would have. Not necessarily the same number, but close. If we add fixed effects related to time, not just linear time, but piecewise time, quadratic time, whatever you need, that should explain residual variance to the extent that time is only within persons. So foreshadowing for next week, all of the examples I showed in the beginning longitudinal class had just time where everybody was on the same schedule, because that's easiest. In that situation, time is purely within persons. But if people differ in where they are in time when they come to you, like if people start at first, second, third grade and they're followed over time, or you have a sample of adults of different ages and you measure them over time, then the longitudinal part takes care of this pile of variance, but the cross-sectional part takes care of this one instead. And those are not going to be the same numbers. So figuring out how to pull apart what is cross-sectional age differences, for instance, versus what is longitudinal age changes. Those are two different sources of variability with two different implications for what they do in the model. But for now, time is just within persons. So that should explain some of the residual variance. If we wanted to allow random effects of within person time, where does that variability come from? It's got to come out of here or here? E. Yep. E splits. Because E is the deviation from the line. Well, if you need your own line, that should make your E variance less. So part of what we were calling within persons is actually between persons. It's buried in there until we pull it apart. In other words, these E's, if there really is slope variance in there, aren't homogeneous and uncorrelated like we expect them to be. So we're trying to pull out some of that dependency further and allow each person to have their own time slope, and then E is what's left after that. So this slope variance then, in adding that to the model, is another instance in which I would not say we've explained anything. We've attributed some of the variability to person change differences, but we don't know why people change differently. Conceptually, it's still error, albeit at a higher level of analysis. So the intercept stays here, but it's conditional on the time slope being 0. So then we have 2 piles of variance at level 2, 1 pile of variance at level 1, and then we get to add predictors to see what makes it tick. So then, this process could be complex and it could be simple based on what kind of longitudinal data you have. If you're doing growth curve modeling, like you have data that look like this, and by the way, it's always growth curves, even if you're going down in a straight line, always. Then the whole thing is, what is the function of time, right? Is it linear, is it nonlinear? Is it continuous, discontinuous? Does it go up and come back down? Does it level off? Like there's all these different kinds of shapes that you can have. And so the fixed effects then are trying to describe the average trajectory. Random effects are trying to describe individual differences in those trajectories. If you're over here, you may not have any random slopes for time or fixed slopes, right? If time is not really important, if it doesn't matter what day, like if it's day 1 of the study or day 2 or day 3, putting in time as a predictor isn't going to help you. But in these kind of data, you have other kinds of things to worry about, and we'll get into this more in the later part of the semester. Like if you have occasions from the same day, those are probably more correlated than occasions from different days, beyond the fact that they're correlated because they all come from the same person. The E variance. Go back to, this picture. We're assuming that this E variance is the same across people. In the context of intensive longitudinal data, so fluctuation kinds of studies, that represents heterogeneity over time, or within person consistency. If some people are more volatile, that's another kind of person dependency that we haven't talked about yet. So believe it or not, there's another kind of random intercept you can have, and it's in the E variance. It's called a scale model random intercept, and it means individual differences in the extent to which you do this over time or this over time. See, the people on YouTube, they don't get the extended cut of the lecture here. This over time, this. This is your tuition dollars at work. That's the only way I can explain it. And like every picture that we've ever tried to draw to explain it is like the visual equivalent of this versus this. But yeah, this idea that everyone like fluctuates the same is kind of crazy from that perspective. But that's what the model starts with. Yes?
And so an example of that, if you were doing a study on mood or something like that, you would maybe try to attribute some of like the big up and downs versus the stable.
On mood, is that what you said?
Yeah.
Yeah, that's a good example.
Or emotion or whatever you want to say. To some sort of level 2 variable like personality trait.
Exactly, like neuroticism. People who are high in neuroticism are more volatile than people who are more, that kind of thing. Yep. Older people, there's research showing that older people's cognitive performance before they start showing deficits becomes more inconsistent. Like variability is sort of a hallmarker of like, okay, something's starting to go wrong in the system here, like that you can't perform something consistently. But there's also a lot of intervention settings in which more consistency is the goal. Like if you're trying to manage your diabetes or other things where you have to like check levels and respond accordingly, then how consistent you are over time is an important outcome. Not just like if you're consistently high or consistently low, but just consistent. So those are extra kinds of things that you would need to consider in those types of studies, where typically in growth curve studies, where you only have maybe 4 or 5 occasions, you don't really have enough information to get at that type of volatility. The growth curve is responsible for most of the volatility. All right. Yeah, hanging in there. Okay, other thoughts or questions on that? Okay. Kinds of nonlinear change. So just a summary slide of all the kinds that we talked about last semester, chapter 6, and there's a lot more out there. So polynomial functions, easy peasy, not that helpful for things that don't come back down after they go up and vice versa. Piecewise functions, I like these a lot for intervention designs or any kind of research design where something happens, like there's an abrupt shift in life. Pre-post pandemic learning, for instance, is probably going to be a thing. Like, how did last year's fifth graders look compared to, fifth graders from 2009?
Federal policy on financial aid.
Federal policy on financial aid, yes. I've been a part of a couple student projects where they were looking at like blue laws, which was like you couldn't open stores on Sundays in certain states for a long time. Yeah, it's a thing. And then all of a sudden you could, and so people looked at all kinds of economic, changes before and after the laws went into effect. Before and after elections, there's all kinds of before and afters that happened in the world. So those are 4 discontinuous things where you're trying to track change during different epochs. We have ways of mimicking exponential change. So models that have truly nonlinear models in terms of the sense that they're not slope times variable, they have like exponential functions and stuff, can be hard to estimate. But you can cheat your way into something that looks exponential by fitting a linear effect of log time. Last semester, I did have an example about this, and we may revisit this, the idea of latent basis. This is an SEM-specific thing, where you estimate factor loadings for how much change has happened relative to 2 anchor occasions. And so you can model all different kinds of nonlinearity that's completely data-driven. Truly nonlinear models, as I said, I can recommend more readings. There's been a lot of development on this topic. There's a bunch of articles on the initial longitudinal class reading list that I added just this last year, or within the last couple years anyway, for those. So I can point you towards things if you have complex nonlinear change to deal with. Because I have an example of a quadratic next week, I want to remind you that you know what to do with a quadratic, right? What's the answer? What do you always have to do to a quadratic slope?
Multiply by 2.
That's it. Multiply it by 2. Because the quadratic slope is half the rate of acceleration of a function. And I have my 2 reasons here why that is. One reason is because derivatives. So if I say that and you're like, yes, you can stop talking now. If you're like, yeah, I had calculus 30 years ago and it's gone, that's me. Hi, I used to be good at it. It's all gone. I think of it this way in terms of interactions. Time by time is a 2-way interaction. A 2-way interaction has to modify each of its main effects. But in these models, there's only one main effect, so it has to modify it twice. I have no idea if that has a basis in mathematical reality, but it makes complete sense to me. So multiply the quadratic slope by 2 to talk about how the linear slope changes per unit time. So we can take a positive slope and speed it up. We can take a positive slope and slow it down. We can take a negative slope and slow it down, or a negative slope and speed it up. Those are the 4 kinds. All right, so we may have more different kinds of between-person variance based on your change function. If we have individual differences in acceleration, we'd have a 3rd circle right here. If we had a piecewise model with 3 different slopes, if you have enough data, you could have 3 different slope variances along with your intercept variance. It's up to you. So then predictors are designed to account for each of the piles, where it is time-invariant predictors for the between-person circles, time-varying predictors for the within-person circles. But what makes the latter complicated is that any predictor that is time-varying probably also has a person dependency to it, too. So like if I add, with stress to the model, and I'm trying to capture, daily stress, to the extent that tomorrow is worse than today, that would explain E-variance. But to the extent that I rate my stress higher every single day than someone else, that's a person thing. That's over here. So any level 1 predictor that is measured, observed like that, is almost always going to go in both places at the same time. That's chapter 8 and chapter 9. All right. Time invariant predictors, briefly. So level 2 predictors, person characteristics, person things. Anything you've measured once, they all get to be centered. So 0's got to mean something. If your time invariant predictor is missing, this is bad. So univariate software, like what we did in Mixed or Elmer, it's going to delete every single case that has missing information. That's whole people if it's missing time invariant predictors. You don't get a choice. If you want to not do that, your choices are bring the predictor into the joint likelihood, which is only possible in multivariate programs. So that's what people would use an SEM approach for. Or multiple imputation within a multi-level modeling framework. Those are your choices. I have never actually done a multiple imputation. I have always done it this way. What are they for? Briefly, time invariant predictors moderate the growth curves. They allow people to start out higher. They allow people to change differently. So if you put in just a main effect, then you're saying that's an intercept shift and it's constant over time. If you put in an interaction with time, you could have something to where people start out the same, but then the group or the time by predictor interaction would spread them out. Or you could have something like this where it starts out differently and changes differently as well. Level 2 heterogeneity is also a thing that you could predict. So location scale models, the idea of predicting heterogeneity of variance. So that was the random intercept of the residual, as well as potentially differences in level 2 parameters. That's harder to estimate. But it may be, for instance, if you have a longitudinal randomized control trial. Let's say that you have a control group and a treatment group and you follow them over time. It's probably the case that the treatment group is going to become more heterogeneous than the control group. Like if you do the same thing to everyone in the control group, they're not going to be as different from each other as the treatment group might be. So maybe we need different G matrices for each group. That is the complicated equivalent to what you learned initially, like in the world of t-tests, right? There were like 6 different formulas for t-tests based on whether you had variance equal, variance unequal, sample size equal, sample size unequal. Same thing. To the extent that groups have different amounts of variance, any test of group mean differences needs to have that built into the model. So, same story. Random slopes are not possible for level 2 predictors. ... There is kind of an exception to that, but it doesn't mean the same thing. It is a correction to a differential heterogeneity problem, and unfortunately, we get to talk about that this semester. I hid it from you as long as possible. But the idea that each person gets their own can't hold for a time invariant predictor because each person only has one value. They don't have their own slope. They have a dot. That's it. Variance explained by time varying predictors. So if it's a main effect, it explains the intercept. If you have an interaction between 2 time invariant predictors, it explains the intercept. If it is a cross-level interaction, level 1 by level 2, then it gets tricky. So if I had something like a group by time, where group is a time invariant predictor, like you were assigned to control versus treatment, if the time slope is random, then group by time explains that random time slope variance. Why do people change differently? Because they got treated and these people didn't. Oh, okay. But if the time slope were not random, then the group by time interaction has to explain level 1 residual instead. Because that's where the random time slope would have come from in the first place. So anytime you're interested in testing these cross-level interactions between a level 1 predictor and a level 2 predictor, a time thing and a person thing, we have to test whether the level 1 predictor needs a random slope first. Otherwise, this is going to be biased. It's going to have too high a type 1 error rates, way too high, if the random slope is omitted. So pseudo R-square is what I tend to use for specific effect sizes. I will refer you to the work of Jason Reitz and Sonia Sturba, who have a whole suite of papers about an R-square calculation that sort of is analogous to pseudo R-square, but also has some different variants. They, of course, have R packages that do all of this. The difference is in the way that it's computed. Rather than start with a model that doesn't have a predictor and then see what the change in variance is after adding it, They stay with the model that has the predictor in it and try to come up with what the variance would have been without it. That's a different way of computing it that makes the variance not become negative, the R-square not become negative. So it solves that problem. They also have a very nice description, I think, much more polite than I would have been, as to why some previous papers did simulations, and it's like, hey, this R-square measure doesn't work. And it's like, it wasn't supposed to work for that. It's like, the residual variance didn't change. Yeah, it's a level 2 predictor, it wasn't supposed to, like that kind of thing. So I think they did a very nice job describing all of that stuff. So I'd refer you to that line of work. Total R-square is an alternative that I also use. This is taken straight from the world of regression. The definition of R-square in a regression model is the square of the correlation between y and y hat. In this context, y hat would be from the fixed effects. You compute what the outcome is supposed to be according to the model, get the actual outcome, correlate those, square it, and then that's total R-square. So it's a way to put everything back together again to describe like the overall quality of prediction, whereas pseudo R-square is how much of this variance did I get? How much of that variance did I get? And it's much more specific. All right, then examples. I don't know if I want to do examples. Should I do examples on a video maybe? Maybe? Because I don't, like, we're out of time. But I've got a couple examples in here. A little bit. Okay. How about I make a video and post that for the rest of this, and that way next week we can start with the accelerated designs that I wanted to. Is that fair?
Okay.
Okay. Questions?
Can you explain slide 63?
Maybe.
Because I have a specific question. 63? Yes, in one of the paragraphs you say, the only way to get to random slopes from 3 occasions is to remove the within-person residual variance.
Yes.
Can you elaborate on that a little bit?
Yes, so it's the same idea that if you only have 2 occasions, and you draw a line between a person's 2 points, how well is that line going to fit?
Perfect.
Perfect. So you can either give everybody the same line and then have some E variance to get to your dots, or give everybody different lines and they fit perfectly. So in 3 occasions, if I have 3 dots and I put 2 lines, how well is that going to fit?
Perfect.
Perfectly. So you can either have 2 different kinds of random slopes or residual variance, but not both.
Okay. Yeah, that makes sense. Thank
Mhm.
you.
Yes, and I just, yeah, the graphic here is my interpretation of papers that try to describe SEM as magic in somehow fixing this problem. They're not magic. They work by constraining the residual variance to be 0, which is a pretty strong statement that your model is like perfect.
Yeah.
So,
Thank you.
sure. All right. Any other questions before we call it a week? Yes, sir.
This is, I guess, going back to slide 45.
45. Yes.
So the main effects of a level 2 variable, those moderate the random intercept.
Main effects of a level 2 variable moderate the intercept. Yes, they do.
So is that intercept, is that where people start in the sense of like at time 0, or just their person-specific average across all the occasions?
If there is, so the question was, does the level 2 predictor moderate the actual intercept at time 0 or just the mean over time? Is that right?
Yeah,
Okay.
and I think it's the mean over time, but I don't know if that's right.
So either way, it works out to be the same thing if the time invariant predictor does not interact with time. Because a time varying predictor interacting with time would allow its effect to change over time, is another way to look at it. Whereas if it's only a main effect, then it's a constant effect. So even if you think of it at time 0, because it's the same effect over time, it's going to stay parallel, just like in this picture. So you can think of it as the mean or time 0 because it's the same effect either way. It's this picture. So like if I said, what's the main effective group? It's here if this is where time 0 is. It's here if this is where time 0 is. So once you have group by time, that allows the effective group to change over time. It allows the slopes to change by group. Then you have the uneven lines to deal with. Yep. Good questions. All right, anything else? Okay, then I believe I have the lecture for next week up, because it's not a lecture, it's a talk. I put up an actual conference keynote address that I was invited to give 10 years ago as next week's lecture. And there's a story behind it too, but I'll tell you that next week. I'm still working on the handout that goes with it, of course. So I will let you know when that is available for probably Thursday's examination. All right, then happy first week of classes, everybody. We made it. Only 28 more classes to go, and yes, I counted. Have good weekends. Let me know if you need anything, and I will see you all next week. Bye, Zoomers.